Hey folks, welcome to Unit 6, where we're going to look at work, power, and energy as a continuation and really an application to the previous units on 1 and 2 dimensional motion, as well as forces. So to start, we're going to look at just work in this video lesson, specifically horizontal work. We're not going to deal with vertical work yet, just to get the base idea of what it is. So the way that we look at work is two different ways. Really, in layman's terms, in common use, if you say, oh man, I have to go to work, usually means that you're exerting some sort of effort, Like those of you that have jobs, okay, I have to go to work. When you go to work, the assumption is that you are going to use energy, You are going to give effort. You're going to try, Or if you do homework, or if you're studying, you're like, oh man, I stayed up and I studied for so long, I put in so much work. But the difference is, in everyday use, the outcome doesn't necessarily matter, You're doing work, so what, You could be saying that you're studying, oh, I put in all these hours, but did you actually accomplish anything? That's really the difference in the transition to how we see work in physics. Work in physics means that there has to be a displacement caused by a force. So what that means is if you push on something, so if you exert force on an object by pushing or pulling it, it then must move as well. So if you push against a wall and the wall doesn't move, you could push and push and push and exert all the force you want, use all sorts of effort, as we would say in our everyday terms, but if it doesn't move, you accomplish nothing, you did no work. If you're trying to pull an object out of the mud, If you're pushing on a car that's stuck in a ditch, if that thing doesn't move, it doesn't matter how much energy you exert, how much effort you put in, how much force you generate. If it doesn't move, you have not done any work. That is the big idea here. So if we look at this example here, we can jump right away into angles, This goes back to our unit on forces. So we're comfortable with forces working at angles. Now notice the difference here, So we have the force of our pull, we have the direction of our displacement, we have the force that's actually doing work along with this unused vertical force in this context here. The reason why that purple vector is unused in terms of work is because only the force in the direction of motion, so the force that's parallel to the motion, is the force that does work. So the blue vectors here, both pointing to the right, that is the direction it's moving. That is the force that is doing work. So that is going to be the force that is causing the acceleration. Think back to our forces at angles. Only the force in the direction of motion was the one that caused the acceleration. Thus, the force that is causing the acceleration is the force that will do work, because that is the direction that it will also be accelerating in. Thus, it's the direction that it's going to be moving in terms of the horizontal or the vertical plane. Now, formula-wise, So the way we look at this is our work, W, equals our force times our displacement times the cosine of our angle theta. Now, work does not get a special unit per se. We can have it simply be the Newton meter, so force measured in newtons, displacement measured in meters. That is also equivalent to what is known as the joule, which we'll see later on is also the unit of energy. And you've probably seen that in chemistry as well. So work is either Newton meters or joules. Both units are fundamentally acceptable. So our force, that is going to be our overall applied force. That angle will then allow us to get to that component that we need. So if we go back to the previous diagram here, the F that is represented in the formula would be the brown or goldish vector here, and then cosine of the angle would then produce the blue vector. So that's what we end up getting when we look at the formula here, So that F is the overall applied force. When you take the cosine of the angle into consideration, that's how we get the force in the direction of motion. And that angle is now specific, It must be the angle between the displacement and the force. That's why it's always going to be cosine. Also, keep in mind, there's a little side note at the bottom here. So F also equals ma, Going back to Newton's second law of motion. So that means work could technically be the mass times the acceleration it is undergoing times the displacement times cosine of theta. Cheesy joke here, Just to preface this one. For some people, work makes them mad, Work equals MAD, work equals mad. Ha 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 ha, right? Terrible joke. But it is applicable here, right? Because if you don't necessarily know the force that's acting on an object, but you know its mass and you know its rate of acceleration, you can find the amount of applied force anyways. This is just kind of a little side note, which you will be able to utilize. So for work, right, we have two ways again that we can measure this, the Newton meter or the joule. Joules, again, being equivalent to energy, because if you have energy, you can do work. And in order to do work, you need to have an energy change. Now, here's a question here. What happens when the force is in the direction of displacement, right? It is only in the direction of displacement, right? So when theta equals 0 degrees. Well, think back to trig, right? What happens when the cosine of 0 degrees equals 1? So our cosine of 0 degrees being 1 means that all of the force is going to allow the work to be done. So as that angle shrinks, right, as that angle approaches 0, that just means that more of your force is going into the amount of work that's done. It makes it easier to accomplish work because you don't need to generate as much force because your angle is lower, right? You can generate a lower amount of force when that angle is shallower to get the same amount of work done. Now, comparably, we then look at our formula here where that cosine of theta drops out when it's at 0 degrees because cosine of 0 equals 1. If you think about this in the other way, right? What if you're at 90 degrees, right? What if the force that you're applying is perpendicular to the direction of its displacement, right? So this would be like if you're holding something up, but you're moving laterally, right? You're applying a force vertically to an object, but you move side to side. No work is being done there, right? There's no work being done. The cosine of 90 is 0. So 0 times your displacement times your force tells you that no work is being done. So when that angle is 0 degrees, all of your force does work. When your angle is 90 degrees, no work is being done. Now, this is an important little note here too. Work is not a vector, right? So displacement is a vector, force is a vector, but what you get out of work gives you an idea of what's happening, right? So it's not a vector, but instead we can tell what's happening for this object when work is being done on it. So for example, right, if you take the sign of work is positive, right? So that means your force is positive and your displacement is positive. That means the object is speeding up, right? It is going to be accelerating, but it's going to be speeding up because the force, the net force, and the displacement are going to be in the same direction. So we get faster. If the sign of your work is negative, right, so that means your force is in the opposite direction that it's moving. That means the object would be, let's say, moving to the left, but the force you're applying is to the right. That's going to cause it to slow down. Because remember, when a force is in the direction of motion, it speeds up. And when a force is in the opposite direction of motion, it slows down, right? The force and the direction of motion have to match in order for them to speed up, and they're going to be opposites whenever we slow down. So here's a quick example to look at. How much work is done on a wagon moving 7.50 meters on a horizontal surface by a 27.4 Newton force applied at 25 degrees from horizontal? Note the wording here. The wagon is on a horizontal surface, and the force is being applied at an angle measured from horizontal. This is a pretty traditional look at how we can find the work that is done. So take a moment, right? Attempt to solve this problem on your own, and then come back to see the solution. Okay, welcome back. Here's the way that we would solve this problem, right? So work equals FD cosine theta. So we have 27.4 newtons of force that we would plug in for F. We have 7.50 meters that we would plug in for the displacement, and the cosine of 25 degrees is going to be our angle there. So our work that is done is 186 Newton meters or 186 joules. Again, big ideas here, big concepts to look at. If this angle gets closer and closer to 0, right, that means that the amount of work that is done is going to change based on the amount of force that is applied. So that angle plays a really important factor here. The closer that angle is to 0, the more work you're doing in the direction of motion. The further that angle is from 0, the closer it is to 90, the less work you're going to do in the direction of motion. So if you take two identical forces and apply one at a 15-degree angle and one at a 70-degree angle, the work done at the shallower angle is going to be more even if you go the same distance. All right, folks, so that's it, right? Just a quick look at work. We will then continue on with other types of work and power and energy. Thanks, guys.